the realms of chemistry and physics. Today I'm going to run through a few undergraduate to upper high school level physics questions, and let's get started. So here's the first question. The mass of Earth is 5.972 times 10 to the 24 kilograms, and its orbital radius is an average of 1.496 times 10 to the 11 meters. Calculate its linear momentum. Okay, so let's set this up. So we've got Earth, Earth, Sun. So the radius here is 1.496 times 10 to the 11 meters, and the mass is 5.972 times 10 to the 24 kilograms. Okay, so first we can calculate its angular frequency. As we know the period, it's not given in the question, but we all know that the period of Earth's rotation is roughly 365.25 days. We'll want to convert that into seconds. So 1 day is 24 hours, 1 hour is 60 minutes, and 1 minute is 60 seconds. Okay, so these will all cancel through, leaving us with per seconds, which is the unit for our angular frequency. So if we run these all through our calculator here, then we get 1.991 times 10 to the minus 7, 1/seconds. Okay, so with an angular frequency in hand, we can calculate, so it wants linear momentum, so we need to calculate not its angular speed, but its linear speed. So that would be its perpendicular speed, or its speed perpendicular to its orbital radius. And we can calculate that with our known quantities, which is omega equals V over R, or V equals omega R, depending on how you remember this formula or find it. So that would be our angular frequency we just calculated, our radius of Earth's orbit, and then this will be our linear speed, or our linear velocity, perpendicular to the orbit. So V is 1.991 times 10 to the minus 7 per seconds times 1.496 times 10 to the 11 meters. And now running these through our calculator, we would get a linear velocity of 2.9786 times 10 to the 4 meters per second. And then I'm just going to move this all up. And so now we've got our velocity. And now with that in hand, we're ready to calculate our linear momentum. So momentum is just P equals mv. And we have the mass, our mass of Earth, which is given in the question as 5.972 times 10 to the 24 kilograms. And then multiplying by this velocity, 2.9786 times 10 to the 4 meters per second. Running that through our calculator, we would get 1.779 times 10 to the 29 kilograms meters per second. And so that would be our linear momentum for the Earth orbiting the Sun. All right, let's check this now with the solution given. So there's our, for the time period, they're just using 365. That's likely fine. And then they're just putting it all together. So rather than expanding the question as I have, just putting it all together into one equation, which is fine to do, obviously. And 1.78, 10 to the 29, so it's pretty much exactly the same, which is great. And so this is correct. And okay, so this question is a bit longer, and some of it's being hidden there, but I'll expand the question so you know when it's being asked. So you stand at the top of a deep well to determine the depth D of the well. So we've got our well, and again we're going to just pretend that's straight. Our well, and there's our water, and we got our little dude standing here, and he drops a rock, and the rock goes all the way down, splashes in the water, and we listen for the splash, which the sound travels up the well. Again, the whole length is D. And so the rock falls initially from rest, so VI equals 0. Its acceleration will be gravity. So it'll be due to gravity, which for these purposes I'm going to use minus 9.8 meters per second squared. And the speed of sound that we're going to use for the sound waves is 342 meters per second. Okay, so we drop the rock and we listen for the sound waves to come back up, and it takes the full time takes 3.9 seconds. So that's our T total. Okay. And so the first question is just to find the quadratic equation for the distance D in terms of the time, the acceleration due to gravity, and the speed of sound. And it wants us to arrange the equations so that there's no prefactor on the D squared term, so which is how we prefer it anyway. So let's start off. So the acceleration is minus g. So this is for the, I'll call it the one leg. And then we'll worry about the two leg afterwards. So the two leg would be the sound leg. So for the first one, the acceleration is minus g. And we're going to use the fact that acceleration is dv by dt, so the derivative of the velocity by time. So that means that dv is a dt, or we can integrate this expression to then get our velocity as a function of time. So if we integrate from v0 up to vt, and in this case we might as well call this first leg t1. So we're going to call the entire thing t1, so I'm just going to integrate it all the way up to t1. dv, and that's going to equal the integral. I'm going to bring the minus sign out front, g from 0 to t1 dt. So now the dv integral is just going to turn into v, evaluated between v0 and v of t1, and that's going to equal minus g. The integral of dt is again just going to be t from 0 to t1. Okay, and I'm just going to bring this up a bit. Okay, so if we do our integration limits here, then we have v t1 minus v0 is equal to, and so when t is 0, the whole thing's going to be 0, so minus g t1. And as the rock starts at rest, right, so the boy's holding the rock at the top of the well, so it's going to be initially at rest, that guy's also 0. So then that means our velocity at t1 is just minus g t1. I realized now that instead of integrating this to t1, because we're looking for the distance, I should have just integrated up to t. So I'm just going to do it as a function of t instead, like this. And I'm going to get rid of the 1s, because we don't need those right now. So ignore the 1s. It doesn't change anything, but just the explanation and the next part of the question. Okay, so I'm just going to leave it as t. So this is now the velocity at any time t during the transit of the rock down the well. The reason why I did that is because, well, now we want to move from velocity to displacement. So our x is, or our velocity is dx by dt. And so then we can get our dx by rearranging this expression and integrating. And so then using this integral, we have integral from of dx from 0 to t, from x0 to x of t is equal to integral minus gt dt from 0 to t. Now we will want to take it from 0 to t1. And now the integral on the left is just going to be x from x0 to x of t1, and that's going to equal minus g, so the integral of t dt, so the power rules are you put it up by 1 and then divide by the power, so it's going to be t squared over 2 from 0 to t1, and then finishing this off, we have x of t1 minus x0 is equal to minus g t1 squared over 2. As this expression is going to go completely to 0 when t equals 0. Now if we take the top of the well as 0, then that's 0. And x of t1 is the depth of our well. But if we are taking the top of the well as 0, then the bottom of the well would actually be minus d. right, as we're moving in a negative direction. So our final distance is actually minus d, so that would be minus d down here, okay? All right, so what we have then is minus d equals minus gt1 squared over 2, or canceling the negatives. Good. Okay, so now we have one expression for the distance d. Okay, and we can solve that for our time as t1 equals 2d over g square root, which is a quantity we will need in a second. So now for our second leg of time, it's just the speed of sound part. So in this case, our velocity is constant, meaning we can express our velocity in our second case as, what do I call it? I call it Vs, yeah, okay. So in our second case, we can call our velocity distance over time, which is just d over t. In this case, I guess I should do it a bit better than that. So in this case, we would call it delta x over delta t, right? So delta x is then 0 minus a minus d, and for delta t, we're just going to call that our t2 time, right? So we're going from the bottom of the well, to the top of the well. So then we're going d over t2. Yeah, okay. Yeah, final minus initial. So the final point is the top of the well, which is 0, and the initial position is at minus d. So it should be a positive d over t2. Okay, so solving this now for our t2, we have d over vs. So now we have our 2 times for our journey, and we know that the total time is 3.9 seconds, and that's going to equal the sum of our 2 times, and so that's this square root 2d over g plus d over v sound. Now, to get our quadratic equation, we could square this right now, but that's going to get messy. So I'm just going to rearrange it as 3.9 seconds minus d over vs equals square root of 2d over g, and I'm going to square this. So if we square that expression, then we would get 3.9 minus d over vs squared is equal to 2d over g, or 2d over g is equal to 15.21 seconds squared minus 7.8 seconds d over vs plus d squared over vs squared. and then just moving this 2d over g inside, we get 0 equals 15.21 seconds squared minus 7.8 seconds over Vs plus 2 over G, all multiplied by D, plus D squared over Vs squared. And then for our final step, we're just going to multiply through by this Vs squared so that there's nothing on the D squared. So then that gives 0 equals 15.21 seconds squared Vs squared minus 7.8 seconds Vs plus 2 Vs squared over G multiply D plus D squared. And then that is now that's our quadratic equation, so that's the answer to part A. And then for part B, it just asks to solve the quadratic for D. So to do that, we're just going to plug in values. So for Vs, we're using 342 meters per second. And for G, I'm using 9.8 meters per second squared. So with that, the quadratic comes out to be quite messy, but still doable. 2.44 meters squared minus 26,537.804 meters D plus D squared. And so then using these numbers in the quadratic equation, we have D is equal to minus B, so that's just 26,537.804 meters over 2A, A in this case is just 1, plus or minus square root of this value squared minus 4 times, okay, I'm just going to actually use a new line for this one. This is just going to end up with me running it into the side. And I'm going to use a big square bracket. So minus, and I'm going to get rid of the square root symbol just because it's kind of in the way as well. So I use a big old square bracket. And minus 4 times 1779022.0.44 meters squared. Close the square bracket to the power of 1/2 all over 2. So this is a little messy, but this is just this value squared minus 4 times that value and times 1. So when we work this through a bit, we're going to get 13,268.902 on this side, and plus or minus the square root of 697,138,955.715 meters squared over 2 on that side. And then taking our square root and dividing by 2, we get 13,268.902 meters plus or minus 13201.695, which means D is either 26,470.597 meters, or D is 67.207 meters. So this, which I would say makes much more sense for the depth of a well, or D equals 67 meters rounded to two significant figures. So that makes much more sense, I'd say, for the depth of a well. So I think that's our answer. Okay, so let's check through this. So dropped at a well. T down is 3. By the time it takes for the sound to travel to the person's ear. The distance traveled by the sound wave. Okay, so they're solving for the sound wave first. And then, so this is the the distance expression that we solve for before. So this is, okay, so plugging in the T down part, okay. Okay. So the signs, but I don't think the signs matter, so that's okay. Okay, so if we now check our quadratic equation here, so it'd just be d squared minus 7.8 times our v sound plus 2v sound squared over g, so yep, that's in there, and then plus 15.21 times our v sound squared. Yeah, so that's exactly the same quadratic expression. And then, so now here's our quadratic equation, which again, they've got everything in there the same. Mine's a bit messier, but it's okay. And so it might be just rounding. I don't know where that value comes from actually. So 2.54 times 10 to the 4 looks like it's probably a mistake, since from my calculator anyway, 15.2 times, oh, they're using 334 meters per second. Okay, so they're using 334 meters per second. The question says 342, so their solution is the likely correct, but for the wrong speed of sound. So I'd say the method is correct. Speed of sound in question is 342 meters per second, not 334 meters per second. But the method's correct, and all the the math is correct. It's just the speed they use is incorrect. Okay. All right. So now for the next problem, find an expression for T1, the tension in the cable that does not depend on T2. So I'm just going to draw this out. So we've got a wall up here and cable, and a mass hanging from this cable, and theta 2 and theta 1. And so the T2 that it's referring to is this one, so that's T2. That's T1. And those tensions must balance the force from the mass. And so to answer this, the easiest way now is to look at the different components of our force. And so we can expand these into similar triangles here. And I'm just going to balloon that up a bit. And so our T1 force will make an angle of theta 1 here because these are similar triangles. So this triangle and this one are both the same, but just flipped. So that's theta 1 there, which makes this T1 cos theta 1 and makes that T1 sine theta 1. Similarly, over here on the T2 side, we will have a similar triangle with theta 2, and this will be T2, and so this will be T2 cos theta 2, and this will be T2 sine theta 2. Okay? And then the force due to the mass is just F equals mg. Okay, so this, check that I didn't mess that up. Okay. Okay, so in the x direction, our x forces everything with force equations have to work out. So in each direction works out independently. So in the x direction we have our t1x plus our t2x plus our t2x. And just in retrospect, I should probably throw in an axis system of some kind here. So there's our y, and there's our x there. So our t1x plus our t2x has to equal our mass times our acceleration x. But nothing's moving. Everything's stationary, so that means that whole side goes to 0. And so t1x has to equal minus t2x. And these are all signed quantities. So in the axis system I've drawn here, the x component of our t1 is this t1 cos theta 1, but it'll be minus t1 cos theta 1 because it acts in the negative direction. So we have minus t1 cos theta 1 is equal to minus, and our x component of our t2 is t2 cos theta 2 from our similar triangles. Right, so this is t1x, and this is t2x, and this is going to be our t1y, and this is going to be our t2y. Now with appropriate signs based on the direction, so t1x is actually going to be negative of that, but they both act in the positive y, whereas this is actually minus mg. Okay, so returning to this. So this is now, we can cancel these minuses, and we'll see what we would want to solve for when we look at in the y direction. So in the y direction, we then have that t1y plus t2y minus mg is equal to MAY, where again, everything's stationary, so that'll cancel. Our T1y is T1 sine theta 1. Our T2y is T2 sine theta 1, theta 2, sorry. And so, and that is going to equal mg, just moving the mg to the other side. And so now what we're looking for is an expression for T1. That does not depend on T2, so it looks like the best thing to do here is to solve for T2 as T1 cos theta 1 over cos theta 2. Now plugging this into this expression down here, we have T1 sine theta 1 plus T1 cos theta 1 over cos theta 2 sine theta 2 equals mg. And now we can rearrange this expression to find the tension in the first cable. And so taking out T1, and I'm just kind of just putting the stuff that has 2's on it together, or dividing by this whole thing, T1 is equal to mg over sine theta 1 plus cos theta 1 sine theta 2 over cos theta 2. And so that's our tension expression. Which doesn't depend on theta on T2. So now looking through the solution here, we want to do our sum of forces in y, and so we can break those down. So that was our final expression we used to solve it. These should be x's, not y's here, but that's a minor error. And so they have to be equal, which is what we found. So you can solve for T2. And then the only thing that they did differently is you can call that tan theta 2 just to simplify things a little bit more. But in the end, their solution, which is mg over sine theta 1 plus cos theta 1 tan theta 2, is the same as ours. So I'm just going to say this solution is correct. Go. Okay, this one just asks, how do we find the magnitude of the acceleration of a particle? So the part that's cut off there is we've got two forces. F1 is 3 newtons I hat plus 5 newtons J hat. And our second force is 6 newtons I hat minus 2 newtons J hat. Yeah. So I hat and J hat are just unit vectors in the x and y direction respectively. So we treat those separately, but we can readily sum up our two force vectors to get our acceleration vector, right? So our F1 plus our F2 is equal to MA. Oh, and it also says the mass of the particle is 3 kilograms. So our force vectors can give us our acceleration vector. So our acceleration vector is 1 over m times F1 plus F2. And plugging in our values for our force vectors here, then it would be 3 newtons I hat plus 5 newtons j hat plus 6 newtons I hat minus 2 newtons j hat. So we can't mix our i's and j's, but we would sum in the i's. So essentially we treat this just like any other variable problem where we have to keep the like variables together. So this would be 1 over m, 3 plus 6 is 9, and 5 minus 2 is 3. And I might as well put in the value of the mass at 3 kilograms there. And remember, a newton is a kilogram meter per second squared. So the kilogram here will cancel with that, leaving us with meters per second squared. So 9 over 3 is just 3. And 3 divided by 3 is just 1. So there's our acceleration vector. Now it wants the magnitude of our acceleration. So the magnitude of a vector is just the square root of the x component squared plus the y component squared, which is then in this case 3 meters per second squared plus 1 meter per second squared. Square root, which equals the square root of 9 meters squared per second to the 4th plus 1 meter squared per second to the 4th, which equals root 10, and just taking the units outside, root 10 meters per second squared. So then that's the magnitude of our acceleration. Okay, so the solution given here is just for the force. So technically that's correct. That is the correct force modulus, but the question asks for the magnitude of the acceleration, not force. Magnitude of acceleration is square root of 10 meters per second squared. And I'm just going to say it's not correct. It's not finished. All right. So for this next question, I guess in this case, which is my 5th, what is the strength of an electric field that will balance the weight of a proton? So if we have a proton and it's experiencing mg, so a force due to gravity, then what we want is for our electric field, our force due to our electric field, which is QE. So we want some electric field which points in the opposite direction, which is going to balance our gravitational force, or to put this in an equation form, we want QE minus mg to equal ma, but we want it to be balanced, so we want no acceleration, so we want that to be equal to 0. So rearranging, we want QE to equal mg, or we want our electric field to be mg over q. So now, using the mass of a proton as 1.672 times 10 to the minus 27 kilograms, the charge on a proton is just the a positive electric charge, so 1.602 times 10 to the minus 19 coulombs. And G is 9.8 meters per second squared. And so then this is 1.672 times 10 to the minus 27 kilograms. 9.8 meters per second squared, all over the charge, which is 1.602 times 10 to the minus 19 coulombs. Electric field should be in newtons per coulomb. Here we have a kilogram meters per second squared, which is in newtons, so that looks good to me. And so if we run through all this, we get 1.0228 times 10 to the minus 7 newtons per coulomb, or, yeah, actually that's fine. And then comparing to the solution here, so we want our electric force and our gravitational force to equal. That can be rearranged. And yeah, so depending on how many units you keep, I suppose there's not really any given in the questions, so it'd be up to the user, but they both look the same to me. So solution is correct. Okay, and so a horizontal metal bar oriented east-west so we've got north and remember that the North Pole of the Earth is not magnetic north, it's actually magnetic south, but that means that our B field on Earth points towards the North Pole. So we've got east, south, west. So a horizontal metal bar oriented east-west drops straight down, so we're dropping it straight down. And an EMF develops between the ends, which end is positively charged. So the easiest way to rationalize through this is to consider the force on a charge due to its velocity. So it'll be V cross B, and this is the force on, depending on the charge, so if it's negative, it'll be in the opposite direction. So this will be the force on this will give you the force direction on a positive charge. And so we can use the right-hand rule here where we, it's likely not possible to see me, but where we point our hand, see if I can draw a hand here, our hand in the direction of the velocity, and then hold our thumb out, I guess. The hand was okay at first, but now it's grotesque. There we go. Hold our palm in the direction of the B field, or we can say that we curl our fingers in the direction of the B field, and then the thumb will point in the direction of the force. And so if we do this for this problem here, so the velocity is pointed into the page, the B field points north, And so our force on a positive particle must be this way, meaning oppositely, a force on a negative charge, so that's the force on a negative charge, will be towards the west end, so the electrons will be pushed towards the west end, meaning that this east end will develop positive charge. And the west end will develop negative charge. But the question asks, which end is positively charged? And that would be the east end. Okay, so here in the solution, pointing the thumb along the motion of the metal bar, which is out of the page. I would not say that, but that sounds more like it's moving up. Fleming's right-hand rule, the direction would be along east to west, which shows the direction of current. So thumb along motion of the bar. Well, in any case, the motion's opposite, which I just wouldn't agree with, but it still gives the east end. So that's, solution's the same, but the motion's different, which is confusing to me, but I'll say the solution is correct. I'm not sure Fleming's right-hand rule applies here. I believe it's for forces on charge-carrying objects, or current-carrying objects, I mean. So I believe it gives you the motion of a current moving through a magnetic field, not necessarily the current due to motion. But I'm just going to say it's correct, mostly because we got the same answer. Okay, so so we have a solenoid of radius 1.25 centimeters. And length 30 centimeters. So a solenoid is just coils of wire tightly wound, so it has 300 turns, so 300 coils over the 30 centimeters, and our current is 12 amps, and our radius is 1.25 centimeters. The question asks us, I probably shouldn't have drawn that, so I'm just going to put length equals 30 centimeters. And so the question asks, what is the flux, the magnetic flux, within a radius or a circular disk, which goes from the center out to 5 centimeters. So first we need to calculate our B field. So the thing about solenoids, or the nice thing about solenoids, is inside the solenoid we have a constant B field, which is going to be equal to our permeability of free space times our current times the number of coils we have over our length. So I guess I might as well put L there. So then they should have, oh, I half did this, but I didn't. So putting in the values here, 4 pi times 10 to the minus 7 Teslas meters per amps times our current, which is 12 amps, times our number of coils, and divided by our length. So we can put in, we can run all these values through and get a B field of, looks like I didn't do the full math there, so I'll rely on the solution to fill in the math. But the point is, but we can work through most of it anyway. So to get our flux, we need our B field within, we need our B field dotted with our full area. And so our area that it's asking for is this one, which would be pi times 5 centimeters squared. But our B field is actually only this value within that radius. And then outside that radius, our B field is actually 0. So our B dot A, which is our flux, is then really our B inside the solenoid, so this B value, times pi times 1.25 centimeters squared, plus our B for outside the solenoid times, and I should just use a new line, plus our B outside the solenoid times that area. So that would just be 5 centimeters squared minus 1.25 centimeters squared. But our B outside the solenoid is 0, so then the whole thing just goes to 0. And so then this is all that matters for the flux inside the solenoid. And then part B just asks to calculate the flux in a small ring, which has an inner radius of A and an outer radius of B. So then in this case, our area is pi B squared minus A squared. And so then our flux is B times this area, where the B and the A in the question are given values of 0.8 and 0.4 centimeters. Okay, so that's not quite as full a solution as I would like, but I didn't work out the numbers there for some reason. But we can still check through the solution here. And so, so now we have our flux as being our B dot A. Because our flux outside the solenoid is 0, that means we only need to use our 1.25 centimeters. And then here's all our values. So that's our permeability of free space, our 300 coils, our 12 amps, and our 30 centimeters converted to meters. And so then this flux here would come out to be the 7.402 microwevers. Okay. And then the same thing here. So we have this same B field, but the area is now this small inner radius. And so we just need to use our outer shell minus our inner shell, which is what's given here. And then if you work through the numbers here, then I presume it comes out to this 2.274. And so the solution is correct. All right, and I'm just going to stop it there and say thank you all for listening and watching. If you enjoyed this, please subscribe. And if you want to leave any questions, there are links in the comments or links below the video. This has been Jeff Krause for OneClass.